So the last chapter in the first part of the book is about recurring decimals. So what I'm really talking about here is when we see 1 divided by 3, we know that it goes to 0.33333 forever. When it gets into a sequence that repeats, we call it a recurring decimal. What I didn't know before this investigation was that there are any number of different length recurring decimals. But the jump that I made in my mind is that the length of the recurring decimal is indicative of geometry. So if we're looking at a 3-digit recurring decimal, we're thinking triangles. If it's 4 digits, we're thinking squares. 5, we're thinking pentagons. 6, hexagons, etc., etc. So I thought, well, I'll just look at the first 99 numbers and see what their effect is on dividing unity. So essentially 1 divided by n, n being the number. 1 divided by 1, 1 divided by 2, 1 divided by 3, what happens? So all of these numbers produce 1-digit recurring decimals. So we know the 3 that we talked about, 6, 9, 12, 15. All of those numbers, when they divide other numbers by it, will give you a 1-digit recurring decimal all the time. Then you've got certain numbers that give you a 2-digit. So if 1 is just a dot, a point, then 2 would be a line, 3 would be a triangle, 5 would be a pentagon, 6 would be a hexagon, etc., 8 octagon. And you can see that, for example, there are only 2 numbers that produce 3-digit recurring decimals, numbers 27 and 37, because those are just multiples of 27 and 37. So the root numbers, only 2 numbers produce those numbers, produce triangles. 7 and 13 are unique root numbers for hexagons, but there's a couple that misbehaves, and this is one. 21 misbehaves. So it produces a 6-digit recurring decimal, but it's the only place that you will see where there is no 2-dimensional numerical symmetry that you see in absolutely everything else. Only the number 21 does this. So whereas we've got 1 divided by 7 is 0.142857, 142857 over and over, and we can see the numerical symmetry there by taking that sequence and doing the same thing as we've done before. But when you do it to the 1 over 21, you get 047619, and you do not get numerical symmetry. And instead of adding to 999, which the pairs will obviously do, it adds to 666. It's inversion. So that's what actually made number 21 stand out in my mind, and that is going to be extremely important in the last part of the book. But there's 1 or 2 more here that I just want to draw attention to. So for example, there's only 1 number that produces a 5-digit recurring decimal, 1 2-digit number that is, which is the number 41. 73 is the only one that produces 8-digit recurring decimals, octagons. 81 produces a 9-digit recurring decimal. 77 produces a 6-digit recurring decimal. Ordinarily, the double-digit numbers, 11, 22, etc., see 77's missing. So there are certain numbers misbehave, and they catch your eye because they're not behaving like everyone else. Everyone else is conforming, so they are the key to understanding everything. Now, if you're looking for a 4-digit recurring decimal, so a square, you actually have to go to 3 digits, and 1 divided by 101 gives you a 4-digit recurring decimal. And this number, 137, which we'll come back to, which is the number associated with the fine structure constant, when you look at that, it produces an 8-digit recurring decimal.